There you go. Stay. All right. Did you guys also hear? So there was the supermoon last night with the lunar eclipse. Right? So hopefully everybody, the water on Mars thing. Yes, cool. Flowing water. They knew water was there, present in certain forms, but they had never. Now they have evidence that actually they haven't seen like a river flowing on Mars. Don't go crazy. But they've seen evidence that water does come out and it forms these little dark channels, and then they dry up over time. The funny thing is, they just never had the resolution to be able to discern something like that until now, and they only have 3% of Mars at that resolution. Do you understand what I'm saying? So that's just the tip of the iceberg, maybe, which is a neat way to put it, but I'll see what happens. I didn't really think that through, but it still worked out. So, all right, so any questions from homework? Yes, ma'am.
Let's see. Chapter 3.7, 12b.
Oh, yeah, is that the freaky one? All right. So let me do this. Let me talk about the idea generally, and then I'll give you some specifics about this problem. Leave most of it for you guys to do. This is number 12 in section 3.7. This is the one that talks about crystals growing in the shape of cubes. And the question is asking you, find the derivative of the rate of change of the volume of the cube with respect to its edge length. So first thing is, so it's asking you to find the rate of change of the volume with respect to edge, with respect to edge length. Now you start to realize why I try to make a little bit of a big deal out of, can you write what they ask you in notation so that it actually informs you as to what the hell to do? Can you give now what do I have to define? I know volume is V. Edge length. Yeah, what are you going to call this? It's an edge length, right? Of course, it's a cube, so it's all the same, so what do you want to call it? That's crazy. Okay. So what in symbols is this asking? dV? dx. Cool. And what they ask you to do is to show that that's equal to half the surface area of the cube. And I think what I'm about to show you will help you see how to look at this. Because the question when you first read it is like, what the hell level do you think I'm at here? But once you see what the idea is, it's actually nowhere near as difficult as it seems. So they want you to show that this is equal to 1/2 the surface area of the cube. And anybody know, what's the surface area of this cube? What's the area of this face? What's the area of that face? X squared. And how many faces are there? So the surface area is 6x squared. So you're going to show that dV dx is equal to 3x squared. So it's half the surface area of the cube. This makes geometric sense somehow. So let me show you an example. I was trying to find an animation since somebody came and asked me about this. And I couldn't find a decent animation, so you're going to get a very indecent one. There's going to be any. Look at that. All right. That's pretty good for me. Doesn't look like Stewie's head at all. So, what's the area of a circle? What's the derivative of that with respect to the radius? dr, right? So with respect to radius, right? So this would be 2 pi r dr, which is 1. I'm not doing it with respect to time. I'm doing it with respect to radius, which means, how does the area change if I pull the radius out? If I pull the radius out, what does the area do? Well, it does this. Let me stop there for a second. Now I really want to make this point. The book makes a better point than I have, I think, with the instantaneous rate of change of the area. Because the minute I change it, what's changed? R. So it's the instantaneous change of the area. So the minute I start to change it, now the rate at which it's changing is going to change. Okay, maybe. We can actually find the acceleration, sort of. We can just take the derivative with respect to r. It's constant, thankfully. But let's not go there. All right, so what the hell is this, though? What is that for a circle? What equals 2 pi r? Yes! So, here's the beauty of this. Can you all imagine, just imagine you have, let's make it a ring, but let's forget about the extra dimensions, right? But we have a circle we can hold in our hands. You with me? One of those stupid magic trick circles. Bing, 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 look, they're connected. All right, go away. You with me? And let's say, so the idea here is if I go a little bit out, and I'm talking about a billionth of a billionth of a billionth of as much as I want, even more than that, I mean just an infinitesimal. So this is delta r, or even better. And let me just say this right now. This symbol, you've seen it before. Sometimes people have seen it in like slope. It means change in. And really it means gross change in. Not like, gross, but crude change in, rough change in. The smaller it is, the more it approaches this, which is infinitesimal change in the radius. The smallest possible change you can make. That isn't zero, right? Let me stop there for a second. And the neat history of this, people had a lot of trouble with the idea of infinitesimals. Like, they don't exist. Go away from me. They're like complex numbers. All right. So if you have your ring, and I want to go out a little bit of the radius, but let's do this really. Let's take some tape and put it around the edge. Haven't I increased the radius a little bit?
Add more tape.
I've increased the radius by how much? If I put some tape around the edge. The width of the tape, which to me, human-wise, is basically nothing, right? But I have. So if I put tape on this thing, put a layer of tape on this thing. Let's see if you do. Screw it. Okay. All right. Ooh, screw it. Yeah, I got a little thick back there. If I put a layer of tape on it, that shape I just made of the tape, isn't that equal to the what? Basically, circumference. So I'm adding to the area that's already there. I'm adding this much. So how much is the area changing? By that much. So when I add tape on it, I am making the area a little bit bigger. I'm making it exactly 2 pi r bigger. Now some of you guys might realize my radius changes a little bit. So if I did it again, I can't really use the same numbers because now my radius is a little bit bigger. But this is all about instantaneous. The minute it's different, it's not claiming it's the same thing anymore. It's like, oh shit, I only worked for right then. Did you guys see that visual? Put some tape on it. How much tape did you just put on there? 2 pi r worth. So of course that's how much the area got bigger. Because that's how much you added to the damn thing. Right? So that's why it makes sense. How much does this change by? By the amount that you freaking added. Now, real quick. I don't see people looking in the faces that I wanted. Because that's kind of neat. The first time somebody told me that, I was like, holy shit, that's cool. I can see that. I can see that. Take the ring out of there, I got this weird loose thing of tape, but that's basically its own little circle. What's the circumference of the circle? Freaking 2 pi r is where it came from. Right? So that's how much it adds to the area. Take a square. Now what's wrong with a square is, notice that I can't use the diameter here. If I actually tried the whole thing, but I put it in terms of diameter, it wouldn't work. So the same thing happens with if I call this S, this whole side length, I can't use it. So I'm going to use this much of it. So let's call this R. Because it's sort of like the radius of the square in a way, right? You guys kind of...
Why can't you use the entire side?
It just doesn't work. So there's an interesting question about what shapes follow this rule. And as long as you find the correct dimension, the correct measurement to put them in terms of, so circles are in terms of radiuses. Why do you think squares also are in terms of radii? Because what's living inside of a square? A frickin' circle. Thank you. So not everything has that property. Are you with me? No. Shit. Well, this is getting a little weird. But this is the idea behind this problem. Let me just follow this through. So how long is this side really?
That's 2r.
2r. So this is 2r by 2r. So what's the area of that square?
4r squared.
4r squared. And what's the derivative of that with respect to r?
8R.
And what is the perimeter of that square?
Or
In terms of r,
8R.
8 freaking r, right? So the derivative of the area did come out to be the perimeter as long as they use the correct measurement. Maybe. Not everything you can think of it as a radius, because not everything is related to a circle, but actually they sort of follow even a rectangle. If I call this 2r to make it a rectangle, I'm going to call this 2r plus 1. You guys kind of with me? Now it's a rectangle, not a square. What's the area of this rectangle?
4R squared plus 2R.
And what's the perimeter of this?
8R.
What's the derivative? Yeah, so the derivative. Get out of there.
8R plus 2.
8r plus 2. And what is the perimeter? Just looking at it.
8R plus 2.
Yeah, it's good. 2, 4, 6, 8 plus 2.
Does that always work?
Second?
Does that always work?
That's the thing. When you get more and more complicated shapes, and in fact, if you want to try to take this into if you want to try to go to 3 dimensions, then you really got to be careful with the shape, and especially if you have some irregular shape. So you got to be careful how far you want to generalize this, but you can generalize it pretty far.
For 2 dimensions.
2 dimensions, yeah, 2 dimensions works pretty well. But I'm talking about if you have some really irregular shape, then you can't really define what r is or something. You see what I'm saying? So it has to be regular in some way. All right, but do you guys get the idea of the tape on the circle? And this is just my attempt. If I just add another freaking rectangle out here, that's why its area changes by the perimeter. Because if you change this radius a little bit, you're just adding like an extra square around it. With perimeter 8r. So that's exactly how much the area is going to change by. Alright. Oh, so this guy. So if you think about this for a second, if you can't draw off 3D, just look at it from one side and realize this is happening everywhere. If this is x, and you don't have to worry about the r and all that kind of shit, it's not going to get to that point. If this is x, how much can you change that? Let's say if I change it by a little bit, what notation will I use for that? Delta x. So that's going to happen on all the faces, right? That's all I'm going to say. That's it. I want you guys to go take it from there. So this is interesting. Do you see how for a circle it's equal to the change in the area is equal to the circumference of it? For a square, the change in area is equal to the perimeter of it. Now this is our first step into actual 3D. So this side changes by delta x, this side changes by delta x. And of course, what else do I have going on here? It goes higher up by delta x. Right, so that's still a cube. So this guy changes by delta x, this guy's got to change by delta x, and this guy's got to change by delta x, so it's still a cube, so it has the same, all the sides are the same length. But do you know how many delta x's did I have to put down there? How many delta x's did I have to put down there?
3.
And does everybody agree with me that that captures everything? If you could take a cube, can you imagine a cube? Can you see it in your head, a cube? And you're able to just pull one face, make it a little bit longer. Now it's not a cube anymore, is it? But if you pull this side a little bit, now it's almost a cube. It's just not tall enough, and you pull this, and now it's a cube again, isn't it? So I only had to change how many things? I only had to change 3. But how many faces are there? 6. Sorry, that last sound effect was completely unnecessary. But I'm going to let you guys see if you can piece it together from there. That's number 12, part B, in section 3.7. As I told the person that asked me about that, that's one of the problems, that if I don't get any questions about it, I get worried about if homework is being done, because that is a weird question. Okay. I think that's all I have to say about that. Anything else from homework? Yeah.
3.648.
Oh, good. All right, perfect. We discussed this, but we didn't really spend a ton of time on this. Is that what it says?
No, it's the other way around.
Oh, okay. I was looking at 50, whatever. Well, that is just a yummy function. You know, like I have a different taste than you, Jeff. There is no way to do this directly. It really, truly isn't. You have to do something because it's a combination of two things. It's a functional base to a power, but it's a base to a functional power. I could take care of either of those separately. I could do any constant to any function I could imagine. I could figure out what that is. Right? In fact, what would the derivative of this be? A to the f of x. Oh shit. What's the derivative of a to anything?
No, 0. That's
So it's itself times ln of a times
The derivative.
yeah. So that I could do. That I could do all day. I don't care what a, I don't care what function you give me, as long as it's got derivatives, I could do it. Or at least one derivative. I could take one derivative. I could do the other end, f of x to the n. I could do that all day.
So would it be sine of ln of x?
But I can't do it. That is both of those. So to use a rule, it has to be in the form of that rule. This is in the form of two rules at once. I can't do that. You guys see it? That's why I have to employ something weird. Does anybody remember what I have to do? Is that what sucks is that stupid thing is up there. I got to take ln of both sides, or any log you want to, really. But we choose ln because it's got one less letter to write instead of log, which is really the truth. So if we take ln of both sides, why is that good? What happens? That comes down, and people get lost in the ln's and shit. You just got to keep them straight. That's ln of this, and because the inside is being raised to a power, that power can come out. And then to take the derivative of this is primarily what rule? Product rule, and then later you're going to see a chain rule, but you don't have to know that right now.
So it's implicit? Is that what
Yeah, now I'm going to do this implicitly. I like it, because now I don't have y explicitly. All right, so this side, what would this side be? Okay, that's as much as we'll do in class. You guys finish the rest of that out on your own time. Unless there's a question related to what to do next. All right. But remember that. I'll teach 280. I bring that back sometimes just to see who remembers and who can pay attention. So be careful if you take me in 280. Anything else from homework?
42 on the same section.
Okay. So notice the instructions. So if I do 42. So here's somewhere else that logs kind of helps us out. Let's go ahead and write that as half e to the x squared plus x. And this is a use that I don't use very often, because what's kind of the easiest rule besides power rule what's the easiest rule? Product rule, right? If I said what's the hardest rule, I think you most would say chain, right? And the next would be quotient. But this would just, do I need to do what they say? No. I could just take this derivative, it would just involve three-thing product rule, right? F prime GH plus FG prime H plus FGH prime. Good Lord, right? Because I got three functions, FGH. Bam, bam, bam. But they say in the instructions, use logarithmic differentiation. Yes, cool. That's exactly what they say. What the hell does that mean? Well, let's take logs of both sides and see why the hell that would help me out at all. So why the hell does that help me out?
Because you can change it to addition.
Yes, exactly. The log of the product. And what's really nice is like the 1/2 comes out, the x squared minus x comes out, and then what's ln of e? And then I get plus 2/3. Yes, sir.
So, but the e
E was e to the x squared minus y, correct?
X, sorry.
Okay.
Yeah, this wasn't some weird
Oh, okay.
implicit. It's
And
all a function of X.
It still comes down, correct? After, because the ln of e is just 1.
Exactly.
So the power comes down as power.
Yeah, when you see this, you can look at it two ways. Log says, what does E need on it to become this? What power does E need to become this? Well, it needs that to become that. So that's the answer to that. Or just, those are opposites of each other, so they kill each other. Either way you want to think about it. But x squared minus x is somehow floating up there. That is the answer to that. Yeah. Cool, maybe. On both of these problems, though, this one and that one, you know what y is. Why is that a big deal? Because right there's y, right? So when you solve for dyx, I don't want to see y shit at the end. You're going to have y shit here and then replace it with that. Same thing here. Take its derivative, we already did. You know what y is at the end, you better bring that back in. Maybe. So you don't see that as often, but you can see why it might be useful sometimes. Made that a lot easier to look at. Okay. Maybe. Alright. Anything else before we get into... Good. Alright, here we go. So last time we had half of this thing left to do still, right? Oh shit, so we just turn you off or on? Very good. Everybody still has theirs, do you? Anybody need a copy of that? You're surrounded by nice people, right? Doesn't anybody here have? Alright, you're all going to look on this. Alright. Wow. The last time we did this problem. And the reason I picked these two semi-specifically is they both have characteristics of most of the problems you're going to see. Hopefully you'll start to see, like up here, what do we have to do? We have to figure out similar triangles kind of thing. Set up a proportion so I can see the relationship between the variables that I have to use. It's all about relationships, which is why they really... So what the hell's going on here? First thing I want to normally do is to draw something. So this is a little weird, but these shadows, because of street lamps or whatever, or the sun, they pretty much have the same idea. So you're going to have I'm going to represent my 6 foot tall woman. She's very skinny. And then here's a street lamp 24 feet off the ground. We'll just put it here. I'm not going to draw them. Well, sure. There it is. Why not? I'm not sure why it's furry, but we'll get past that.
It's a light.
Yeah, there you go. Now her shadow, how long will her shadow be, and geometrically why is it that long? And you don't have to tell me the length of it really, but how do I determine visually how long her shadow is going to be? Draw a straight line, right? So the reason the shadow exists is because the light hits her and it can't show up here. So right above her head, the light's going to hit the ground there, and the rest of it's going to be because she's in the freaking way, right? The light's not really upset about that, I don't think. M. Night Shyamalan's going to make some weird movie about light getting back at us. You're in my way. Sorry, if you've never seen The Happening. What's happening? Yeah. Trees are tired of this, man. All right, I'll stop. Sorry. All right, so two of the main things with related rate problems is drawing the picture correctly and then choosing your variables and where they are correctly. And very often there's more than one way to choose your variables, but you want to be consistent. So looking at the questions, how fast is the length of her shadow? So probably want to have a variable related to that. So what do I want to call this here? That's crazy. I
We're
like it.
looking at dx dt.
Say again?
We're looking at dx dt.
For part A, exactly. And now I also have kind of, do I really care about this specifically? Not that I know. So I'm going to call this whole thing y, which would make this what? Y minus x. There it is. Total minus the piece, right? Let me stop there for a second. So that's one place I could have called that y minus x piece. I could have called it y, and then the long one would have been x plus y. But as long as you're consistent, you're going to come out with the same answers. Sometimes there's a way to define it so that the math is a little bit easier. But most of the time, you don't know ahead of time what's going to make that happen. So, oh well.
So is her rate to change dx dy? I mean dx dt?
So the first question, and real quick, what's the last thing I could put on here?
24.
Yeah, this is 24. And it stays 24 as far as we know. Right? It didn't say that the light started to sink. A sinkhole, that would be a good one. A sinkhole opens up below the sleeve. Sorry. And it's descending at a rate of 1 foot per second. I'm getting ideas. So what's the symbol I can use for this? dx dt. Right? This is all about rate. This is all about per second. Right? This is all about per time.
Is it always going to be time? Yeah. Or do ours?
Like we saw up here, we did, it's not there anymore, but we did derivatives with respect to r. You could do, it all depends on the way they ask you in the question. You could do derivative with respect to the angle.
Well,
Do you see them? So then all your stuff will have to be in terms of angles. Right? So you got to be careful. And normally you can kind of tell by what they tell you. 4 feet per second kind of gives it away. This thing should be brighter. Alright. So let me stop there for a second. You guys doing okay? I don't know if anybody tried this problem yet. If you did, you might have labeled things differently. Right? But as long as you identified what you need to label, that's what's important. Okay, well, now in symbols, so this is what they're asking me. What is it they tell me?
Well, you have her rate of change
walking rate.
And as she's moving, what's changing?
her shadow.
The angle with the light.
Well, no. When she moves,
The angle with the light.
don't overthink it. Those are all secondary effects. She is walking. What is changing? Yeah. So, now let me see if you guys agree. I sort of did this, not really, I can't say I did on purpose. Do you think our choice here is smart then to call this y minus x? Or should we maybe call this y and call this x plus y? I think at the end it really doesn't matter. But I'm starting to try to say, do you see why maybe right now it seems it might be better to call this y? Because then what is it they ask that they give me? That 4 feet per second would be, if I call this y, that would be dy dt. Much cleaner than dy minus x dt. That gets a little bit freaky. We might run into that problem later, but at the moment, I know that's a problem I can take care of very easily. So if we call this y, what's this going to be? X plus y. Yes. So we'll see if that becomes a problem later. So then this is dy dt. So very often students are focused too much on the specifics. What's really important is, like I said already, drawing the picture, identifying the variables you got to use, what do the variables represent, and then identifying a notation based on the variables you've picked. In notation, what is it they're asking you, and what is it that they've told you. If you can do all that, even if you have no idea what the hell eventually to do with this shit, maybe then you'll see what to do next. Right? The more you can write down, the more you can see what's the next step.
Would it be dy dt is negative 4 because it's decreasing?
Good. Well, yeah. So we can put a negative there. I like it. Cool. Since y is officially this length, it is decreasing. It's getting closer. Good catch. I like it. All right. So then, for part A, what relationship is there between x and y? Something. Now, there's one last thing in here I haven't labeled.
6 feet.
Yeah, she's skinny, but she's 6 foot tall. Good. So I like this because this happens decently often enough that I thought it was okay to put two problems that have the same kind of thing. You got similar triangles here, right? So what relationships can I set up? Holy crap! So 6 is to x, as 24 is to. Alright, cool. And that we can actually kind of solve for x, because that's what I want to know eventually is dx dt, right? We're trying to solve that for x. So let's see. If we do that, we'll get 6x plus 6y equals 24x. Is that cool? And then subtracting, get 18. Divide by 6, you get y equals 3x. Okay, is that all right? 6x, 6y, subtract 6x, you get 18, divide by 6, you get 3. Cool. Okay, and now you've got everything you need, because we have y equals 3x. We know that dx dt. We want to know, I forgot I was going to, it doesn't matter, we're close enough. We know what dy dt is, and we want to know what dx dt is. So I've got everything I need, right? So the derivatives of this would be what?
dy dx.
dy dt.
Oh, dy dt.
dx dt. You take the respect to t of everything, right? I know the rates of change over time for everything. So everything's just going to be over dt. So I get d. What is dy dt?
-4.
-4 equals 3 times that. So just divide by 3. So I get -4/3. So the rate of change of her shadow's length is -4/3 of a foot per second.
So but that's. Oh, so that only means that it's increasing by like a foot and a third, but in that direction?
Well, it's decreasing. So as she's getting closer to the lamp, what's happening to her shadow, of course? Have you guys ever done this? You're walking behind somebody with a flashlight and you annoy them? I know I have. Where you put the flashlight up and down and they like become small and huge and small and huge. Have you never done that before? Or something like it? Have you noticed as you walk away from a street light, your shadow gets longer, of course, right? Of course it does. And there's the geometric reason why. As she gets closer, it's going like this, the triangle, and then this piece is going to get smaller and smaller. Until, of course, she's right underneath the light, and then where's her shadow? And she ain't got one. She's in the way of her shadow, right? Then the shadows attack. They get tired of us getting in the way. All right, let me stop there. So you have a problem in the book. I'm not suggesting it's going to work exactly like this, but it's going to involve similar triangles. It's going to have a very similar setup. Maybe. All right. And do you notice I didn't have to tell you anything about what the lengths actually are at the moment. I didn't have to say at a time when she's 7 feet away from the street line. And why didn't I have to tell you that? Because when I did implicit differentiation, did it depend on x or y? Is there an x or y dependence here? No, it's only a dy dt, a dx dt dependence, right? Maybe. Like the other day we did, what was the one we did? I can't remember. So if we had 4/3 pi r cubed, during that would be 4 pi r squared dr dt. So it's got r squared and dr. I got to know the rate at which the radius is changing, and I have to know at what radius am I talking about. But here it's a linear relationship. It's nice. It's a constant change. It doesn't depend on how far away she is. It's just changing at the same speed. So how about the second piece here? This is kind of evil, because some of you guys might feel like we've already done it. But this is the length of the shadow. The tip of the shadow is related to what? When the tip of the shadow moves a little bit, what actually directly changes?
X plus y.
X plus y. There you go. If the tip of the shadow moved a little bit in, this changes. X plus y changes. So I'm looking for, this is the question about dx plus y dt. Which is actually not that hard. I don't know why I was making a big deal out of it earlier. But just to show you have some flexibility over how you define things. You totally do. So dx plus y dt. How do you do that? You guys know. I think it might be just the way it's written. But how do you take the derivative of x plus x squared? What's the derivative? Alright, so let me write it like this. So it's dx dx plus dx squared dx, right? It's just 1 plus 2x. You do each one separately, don't you? You can take the derivative across summation. So the derivative operator sometimes acts like it's linear, which means it looks like it distributes.
So is dy dt the same?
Well, dx plus y dt is what they're asking me, right? I got to start there. And then I can write this as dx dt plus dy dt.
So it'd be -4 minus
Good.
-4/3.
So dx dt is -4/3. And dy dt was given to me as -4. And what's that? This is also known as negative
5/3.
5 and
1/3.
1/3. There it is. Crazy. And think about it. Why does that make sense? Well, I don't know if I want to do this right now. Today's Monday. Got a little more time. You could put specific numbers in there and just see, like we did the other day, and say 1 second later, what does it look like? But of course, as she gets closer, as she walks closer, this is getting smaller, but so is her length of her shadow is getting smaller. So then this is the sum of the effects of those two things. Did I have to know that going into that? No, I didn't have to know that going into that. That's why math itself explains things very often. That's why when I taught physics once, Physics 100, where they didn't know any math, basically, or they didn't have to know any math, I hated it. Because you have to use math to explain something fully in physics. You just do. So I was like, oh shit. Anyway, so I'll never do that again. Alright. Yes, sir.
Just out of curiosity, for these types of questions, do you want it as a positive value because it's just asking how fast is it moving, or does it matter?
Yeah, that's why in this case you didn't have to. In physics and these kind of things, negative just denotes a direction.
Yeah.
Because this should hold even as she's moving past. If I move past the lamp and keep walking, these have to still hold. So by putting a negative, you're actually just saying that direction is negative, which actually is sort of like the opposite of what we think. But I like the point was in this at this instant, it is getting smaller, so we could call it negative. But what we really did is we called this direction negative. So once I call that negative, that's why that came out negative, right? So even if I called it positive, then this would have been positive, and I would have still gotten 5 1/3. The direction is just an extra thing. That's really the sign here, just tells you direction. I like it. Okay. So, here you go. You ready? So, in the interest of saving trees, I didn't make you copies of this, but I want you to try these. And just to warn you, I really, really like these problems. Which means they might be a little bit interesting. Please work together. If you really don't want to, okay, that's fine.